Hi, now that you know the most accurate theory of how electron came to life, let's get into electronics. But not quite yet. I can't just tell you what the voltage and current are. The video would be too short. You won't quite grasp the meaning. So when scientists were discovering electricity, they already knew mechanics by heart, and that's how they were quantifying electronics. Mechanical science is the first thing any creature is exposed to right away. Although our bodies are advanced in mechanics, electronics, chemistry, and computer sciences well beyond our understanding, all we can really learn right away is mechanical science, picking things up, making tools and such, no matter if we are tiny crabs or humans. So let's learn some basic mechanical physics. And what's physics without mentioning one of the greatest men the world has ever known, Edmund Halley? He was an all-round scientist with his own discoveries and inventions, but his greatest discovery was Sir Isaac Newton, one of the greatest scientists ever. Halley talked to the super introvert Newton and realized that Newton had years of unpublished discoveries. Newton already knew that the gravitational force between two masses was proportional to the product of their masses divided by the square of their distance. Halley made Newton write his knowledge and publish them for Newton at his own expense. He gave Newton and his science the recognition it deserved, and with this helped make a big leap in science. Halley was a great man. He showed us that you don't need to be great at something to make a big difference. All you need is to find brilliant minds without discrimination and give them the ground they need to grow. And for that I salute thee. In his book, Newton provided his three famous laws of motion, and the second one states that the sum of all forces on an object is equal to its mass times acceleration. And for that, Newton was picked as the unit of force in his honor. Later on, James Watt, the great inventor of steam engine, developed the horsepower. Every horsepower is basically the amount of weight a typical horse can pull up by 1 meter every second, which is around 75 kilograms for metric horsepower. That way he could compare the strength of his steam engines with the equivalent of horses. Then James Joule came along and said, let's do it properly. Horses are kind of random and horsepower really works for Earth's gravity. On the moon, horses can pull a house. The work done on an object would be equal to the force applied to it, which is mass times acceleration, times the length of distance that object travels under that force. The work would be the energy spent by that force to move a mass by a given distance. We need a unit for this. Joules. Then Joule said, now that we have a nice way to calculate work or energy, let's divide it by the amount of time the energy was spent, and we will have the work done in 1 second, which is the power. So if a certain amount of energy is spent in less time, it has a greater punch. And in honor of James Watt, the unit of power shall be known as watts. James Watt. And then people became interested in electricity. They had already seen thunder and electric eel and knew that you can make this magic attracting force rubbing amber against fur. These are just some pieces of napkin and a plastic ruler rubbed against animal fur. But nobody cared until later in 16th century, the cool boy William Gilbert did some study on this new force and called it like amber in Latin, or electricus, which later became electricity. Also, a century and a half later, Benjamin Franklin proposed and allegedly performed his famous kite experiment. Well, don't do it at home. You can't do it at home. Just don't do it. Ben's proposed lightning rod experiment killed Georg Wilhelm Richmann back in 1753. So I make Benjamin Franklin the honorary Electroboom board member. Then Charles Augustin de Coulomb came along and said, well, obviously there is something flowing inside a conductive medium like a fluid. Let's call that electric charge, shown with a Q, with the unit of, you guessed it, Coulomb. Coulomb did an interesting experiment to measure the force between two charged balls. See, for example, if I put some known charge on my ruler and bring it close to my pendulum, which is made of a ping pong ball, it will attract the ball. If I know the weight of the ball and how much it moved, I can calculate the force imposed on it by the electric charge. Coulomb did a similar thing with two charged balls, one of which was twisting a spring-like string. From that experiment, he inferred the Coulomb's law, which states that the electric force between two static charges is proportional to the product of their charges divided by the square of their distance. which is very similar to Newton's law of gravity. Later, Coulomb1 Amperes, a teacher and scientist, did a bunch of experiments and realized that if we pass electricity between two adjacent wires, they impose a force on each other, like this. The electric current, which in this case goes in the same direction, results in the wires attracting each other. Oh, too much current. So the unit of current is named ampere or amp in honor of his research and is shown with a capital I. The definition of current is if we have two very thin parallel and infinite wires 1 meter apart, 1 amp is the amount of current through these wires that generates 2 times 10 to the power of -7 newtons of force per every meter of wire. Very small force. I was hoping for a better definition, but whatever. Understanding electric current is easy. Imagine a water hose and you could measure the flow based on the amount of mass passing a point in the hose per second, like 1 kilogram per second. 2 kilograms per second would be more current. We can do the same thing for electric current, except here mass or volume don't matter. Electricity can move with tiny electrons or large ion particles in solids, liquids, or gases. What's important is that it's the electric charge that does the electrical dirty work. So the electric charge in Coulomb passing through a conductor every second is equal to the electric current. And therefore, 1 coulomb is defined as the amount of charge that 1 amp of current can carry every second. Of course, back then, they didn't know that it is the electron passing through the wire. All they saw was that the electricity flows between opposing charges. So they called the charge on one side positive and on the other side negative and said the current flows from positive to negative. Later, based on this definition, we figured that the electrons are actually negative and move reverse of the defined current flow. But that didn't affect the science and calculations. And in fact, sometimes we can argue that it's the positive ions that carry the charges. So we stuck with the original definition. In the meantime, Alessandro Giuseppe Antonio Anastasio Volta came along. He made the first battery called voltaic pile, which of course was well after the Baghdad battery made by aliens to power pyramids. His battery was a source of electrical energy. If you connected a circuit across it, it would provide the energy that would push the current through the circuit. Back to mechanics, if I hold a mass above a surface, the force applied to it is equal to its mass times the gravitational acceleration of Earth, or g. If I let go of it from a height of h, it releases an energy equal to the force times distance, or mgh. But if I don't let go, this mass has the potential to release that much energy. Similarly, if we have two charged balls like in Coulomb's setup, we know how much force is between them from Coulomb's law. And knowing their distance, we know the total electric potential energy they would release if let go. Now the interesting thing is that the total energy doesn't affect the current. It's like you're holding 1 kilogram of water at a certain height or a huge ocean of water at the same height, and all the water has to go through a single pipe. The water would still have to go down 1 kilogram at a time, and the current would be dependent on the gravitational acceleration and the height that the 1 kilogram has to go down through, which is basically the total potential energy, mgh, divided by mass, or just gh, which is called the specific energy. Same thing in electronic. The electric current is not dependent on the total energy, but the available energy per unit charge, or joules per coulomb. And the unit for this, in honor of Alessandro Giuseppe Antonio Anastasio Volta, is named volt. Voltage is also known as electric potential, and the voltage difference between any 2 points in space is the difference between their electric potentials. After all is said and done, I just want you to remember these. Voltage is the amount of energy in joules available to move 1 coulomb of charge, and current is the amount of charge in coulomb passing in 1 second. And when the voltage value of one point is higher than the other point and there is a conductive path between them, the positive current runs from the higher voltage to the lower. That's all. Remember these and I'll see you next time. But James Maxwell, man, he wrapped the whole thing in math. And where were women when all these great men were shaping the world? They were busy being discriminated against, fighting to get their basic rights. They were not even allowed a proper education, forcing into doing what a woman should do. You remember I was talking about finding brilliant minds without discrimination? World would be a much better place. We would be way further ahead without discrimination. Don't do it at home.